And we did the integral test, and now we're doing the comparison test. We're not doing MCQ Monday this unit. Forget it. Okay. Unless you want to. Yeah, I figured you'd want to. No, don't you miss it? Oh, God.
Maybe like one or two.
Just one question? Yeah.
No, like one thing.
One thing.
You don't get rusty.
Yeah. Okay, we'll do that.
Midway.
We'll do that. Well, we'll do that next unit. Wait. When's the test? Friday. Yeah. Okay. Yeah. All right. Just to review real quick, do you know any convergent series? Do you know any series that converge? Do you know any series that diverge? How about this one? Is this true? Does that converge? 1 after the n. Yes, that's geometric where r is less than 1, right? So, what about this one?
No.
Right? That's correct. It diverges, right? N is greater than 1. Okay, how about this one? 1 over n squared. That's a p series of p is greater than 1. That is convergent. And how about this one?
No.
What?
Wait.
That's a p series where p is?
Yeah, it is.
1/2. When p is 1/2, it's divergent. Okay. What about the alternating harmonic as opposed to the harmonic? Or this one blows up. 1 plus 1/2 plus 1/3 plus 1/4 plus that blew up. But when we alternate the signs, we're actually adding and subtracting, and actually converts to something. This one hasn't come up yet, but let me throw it in while we're at it. 1 over n factorial. It converges to E. Interesting. This converges to ln2. This converges to E. If you start with n equals 1 here, and if you start with n equals 0 here. And what else do we know to diverge? Anything that fails Cauchy. Anything that fails Cauchy's divergence test will diverge. So we have a huge grab bag of series that we know to converge or diverge. This is what we're trying to build up. So that we encounter these things with power series, this will be an easy task whether to figure out if something's convergent or not. Okay? So any geometric series where r is less than 1 converges. Any p series where p is greater than 1 converges. This is one special series, the alternating harmonic. This is one special series, the inverse factorials. How many series am I talking about here? This is only one. This is infinitely many. As long as you pick an r that's what? Less than 1 in absolute value. I could put in like negative 1/2. I could put in positive 1/4. I can put in positive 5/6. I can put in negative 8/9. As long as this thing is less than 1 in absolute value. So that really that's really representing infinitely many different series you could choose, right? Likewise here, this represents how many series? What do I mean by this? Do I mean one series? Yeah, Cauchy? No, Cauchy. Yeah, Cauchy. Yeah, Cauchy. All right, anyway. What am I saying here? Am I talking about one series? No, I'm talking about infinitely many series. As long as P, in this case it's 2, but P could be anything greater than 1, actually. Greater than 1. All right, so 1/2 is bad. N to the 1/2. Rad N. Okay?
What if it's negative?
What if what's negative? The exponent? Then it's not a P series. It has to be, the power has to be in the denominator for it to be a P series, okay? All right, so that's just a brief summary of what we've seen so far. And we talked about the integral test last time. So now let's talk about the comparison test. Now remember, the integral test is convenient if your function that you get when you convert all the n's into x's, remember that stuff last week, right? If the function you get is continuous and it's decreasing and it's going to 0 and you can integrate, but what if you can't integrate? What if you get something you can't integrate? Or you get something that you can't differentiate because you have to do that f prime thing to figure out if it's decreasing, all that stuff. What if you can't use the integral test? There are other tests. All right, so let's talk about the comparison test today. What if I gave you this series? Okay, so what do you think about this series? Does it converge or not? How do we know? You don't need the integral test. You don't need the comparison test, actually. This should be glaringly obvious. Does it converge, Ethan? Right, which one blows up faster? Exponential or power? Exponential, right. So it's top heavy. So the terms that you're adding up, are they getting closer and closer to zero? No, they diverge. This does not pass Cauchy's. Right? Cauchy's minimal criterion for convergence of series of all positive terms does not apply or it fails. All right? So now remember, here's a little mnemonic, NN Feppel constant. What? Yeah, it's real catchy. NN Feppel. Mnemonics are supposed to be easy to remember, right? Yeah, sure. Okay. NN Feppel constant. It can be shown that for n sufficiently large, n to the n is always greater than some factorial. It's always greater than some exponential. It's always greater than some power. It's always greater than some log. It's always greater than some constant. Okay? By the way, it doesn't have to be 2 to the n. It could be 3 to the n. It doesn't have to be n squared. It could be n to the 5th or something. Whatever. Some power, some exponential, some factorial. Okay? This kills off everything because it's at the same time exponential, the variable is in the exponent, and power, the variable is in the base. This kills off everybody. Anyway, what do we have? Exponential over power. Exponential grows faster than power for n sufficiently large. At that point, for infinitely many n, it overpowers, in fact, n squared. So divergent by Cauchy. Does not pass divergence test. What, where, who? This? They're all n's. Everywhere, when in doubt, it's an n, okay? N. I don't care. Okay. ln. That's n. That's n. That's n. Yeah. Okay. So, it does not pass the divergence test for Cauchy, so forget it. You don't have to apply any test. Good. All right, what about this one? N can start wherever it wants. It can start at 0, it can start at 1, it doesn't matter. What's your intuition? Do you have any intuition about this? Does this look like any series that you already know? And therefore you know if it converges or not. It's a lot like 1 over n, isn't it? Let's see. How does it compare to 1 over n? How do the terms compare? Let's say I start with 1. So half plus what? 1/3 plus 1/4 plus, right? What about this one? Wait, one at a time. Wait. Plug 1 plus plug in 2 plus plug in 3. So look, all the terms I have over here, well, why is that red? Stop that. All the terms I have over here are smaller than all the terms I have over here, right? 1/5, 1/4, 1/6, 1/5. So if the numbers I'm adding up here are smaller than the numbers I'm adding up here, this sum is bigger than that sum, isn't it?
Wait, don't you face all the way around? That's the 1. Yeah. Isn't it all the way around?
Yeah. Wait, hang on. Wait. The denominators here are... Yeah, that wasn't helpful, was it? That didn't help. Whoops. Okay. Not good. Not a good comparison. Yeah, hang on. Wait, not a good comparison. See, the game is this. If you can show that this is always bigger than something that diverges, that you know already diverges, it's got to diverge. If you're going to show that this is smaller than something that converges, you already know that it converges, that's got to converge too. Aha. That wasn't a good substitution. Okay. The idea behind, the idea behind this is to, why is this not looking right? Oh, okay, yeah. All right, what about this? How does this compare? What did I do? I replaced a constant with a poly from NN Feppel constant. If I replace a constant with a poly grows faster or slower than a constant? Faster. So these denominators are larger. So the fraction is smaller. That's what I wanted.
Which means that they both diverge.
Well, if you can show this diverges and this is bigger, then this diverges. I don't know this, but I do know this because is this the same statement? Exactly. Is that the same thing?
Oh, yeah.
2 times every n downstairs, right? That's n plus n. So 1 plus 1, 2 plus 2, 3 plus 3, or 2 1s, 2 2s, 2 3s, right? Now, this apparently is smaller than this. This is known to explode, exactly. Diverge, right? This is harmonic. So this blows up, and this is bigger. Blows up. That's the game. Use NN Feppel to replace what you've got to make the denominator smaller. The denominator bigger to make the whole thing smaller, or vice versa. Play around with this in such a way by substituting stuff from NN Feppel so you get what you want, what you think. You have to have some intuition already. All right, so is that true? Well, let's see. This is going to, if we start at 1, this is a half, and we start at 1, this is a half. Plus, then you plug in 2, and you get a third, but now we get what? A fourth. And here we plug in 4, we get a fourth. But here we plug in, we plugged in 3, we get a fourth. Here we plug in 3, we get a sixth. Right now, the first term is equal, but every term after that, for infinitely many terms, these numbers are smaller than these numbers, so you're right. So what's your conclusion? Remember, you have to write a conclusion for these tests, just like the integral test. What was the conclusion last time? Therefore, this series diverges by comparison to a harmonic. Therefore divergent already, I said that. Right. Therefore divergent by comparison to a harmonic. Damn it, it's red. Okay, there you go. That's it. If you can show that it's always bigger than a harmonic, it's got to blow up. That's what we did. Okay? So if you can show it's bigger than something that blows up, it blows up. If you can show the unknown series is smaller than something that converges, it converges. Okay? There we go. Let's try that again. What about this one? Three to the n. 3 to the n. All right, so what do you think? First of all, does it pass Cauchy? Is it bottom heavy, in other words? Yeah, the terms are getting smaller and smaller, right, as n gets bigger and bigger? All right, so it passes the divergence test, so it may converge, but it doesn't mean it has to converge. And how do you know that? Because NN Feppel, right? We have poly, and we have exponential. Exponential grows faster, and then Feppel, right? So this is bottom heavy. All right, so it passes Cauchy. Now what? Do you know any series that has this kind of a term in it that you can compare to? Any ideas? Doesn't this look a lot like a geometric? What if it was just this? Isn't that a geometric? First term would be what? 1. What's the common ratio? What do you multiply by to get every subsequent term? It would be 1 plus a third plus a ninth plus a 27th. What would it, if A is 1, remember the first term is called A. The common ratio R, is it less than 1? What is it? What am I multiplying to get this? What am I multiplying to get this? What am I multiplying to get this? It's always a third, right? So this equals A over 1 minus R. 1 minus 2/3 is, 1 minus 1/3 is 2/3. So 3 halves, right? Remember this? So if it was this, I know already it's done. It's geometric and converges to 3/2. But it's not this. It's this. That complicates things. But can you make it look like a geometric by comparison? What if I replace the numerator with an exponential? What did I do? Did I make this a greater than or a less than? What's the relationship between poly and exponential? Less than. Right? But isn't this in turn geometric? Who's the first term?
How do you know it's 2?
I just picked an exponential.
Same thing that we just did on that one too.
Well, yeah, because it's this. In other words, this is just 2/3 to the n, isn't it? So who's the first term? Plug in 0 and you get something to the 0 is 1. Who's the common ratio? 2/3, right? Because you get 1 plus 2/3 plus 4/9 plus 8/27 plus, right? So the common ratio is 2/3. Is R less than 1 in absolute value? Is the common ratio 2/3 less than 1 in absolute value?
Oh, yeah.
Yeah, it is. So this converges to stuff. Well, if this is smaller than something that converges, what can you say about this? It's got to converge. Okay, so there you go. Therefore, convergent by comparison to a geometric series where R is 2/3. All right, that's how you state the conclusion for these. Well, is that the only way you could have proven convergence for this series? Look at this other way. The same idea, though. What if I did this instead? Let's see, what would be good? I'll change the denominator. Now, what did I do to the denominator? I went from from exponential to poly. Wait, hang on, you'll see why. I went from exponential to poly. So what did I do to the denominator? Did I make it smaller or larger? I made it smaller. So I made this whole thing. If I make the denominator smaller, the fraction is larger, right? So can you say less than still? If I made this whole thing larger, right? This is less than, yes? Well, why is that good? Why is that good? Don't you know this series? Who is this? That's a known convergent series. Who? This is who? That was geometric. This is what? You forgot already. P series. Therefore, this thing converges by comparison to a known P series. It's known to converge because P is who? 2. Right? We showed previously using the integral test. Right? All P integrals that came from P series like this, if P is greater than 1, this converged. We did that Friday. We'll get your notes on Friday. Okay. What about this one? Ready for another one? All right, just practicing scrolling up. Who said scroll up? Just practicing comparison tests today, right? And the game plan is to use the NN FEPL to replace stuff in the denominator with smaller to make the thing bigger, or replace stuff in the denominator with bigger to make smaller, or vice versa. Replace stuff in the numerator with bigger stuff to make the whole thing bigger, or replace stuff in the numerator with smaller stuff to make everything smaller, or a combination of both. Play around with the numerator and the denominator if you have to. All right, here's another example. first of all, the first thing you always ask is, does it pass Cauchy?
Yeah.
And it must, because n to the n is the notorious function that grows faster than everybody. So 1 over that, it's got to get closer and closer to 0. All right, which makes it easy to do by comparison. You can compare this to anything, and this denominator will always be bigger, right? Compare it to anything on the list. That's unfortunate. Why did you do that? Look, what if I compare it to an exponential? Now remember, n Feppel, this is the biggest thing, so this is smaller. If I made the denominator smaller, I made the whole thing bigger. Right? Now, this test would be inconclusive. This test would fail if I showed that something smaller than something divergent. Is this divergent or convergent? Convergent. It's who? What kind of series? You know it already. Geometric. That's a geometric series. Okay? All right, so you're done. Therefore, this series, got to name it. Convergent by comparison to geometric series. And what makes it convergent is that R is, who's R? 1/2. R in absolute value has got to be less than 1. R is 1/2. You're done. Okay. Could you have done it differently? Sure. You could have picked anything you wanted down here. What if you replaced this with, I don't know, a poly? Like, try this. How do these compare? Is it less than, greater than? It's less than, because remember, this overpowers everything according to n Feppel. It overpowers power. So this denominator is smaller than that denominator, makes this whole thing bigger. Okay, why is that nice? That's a p-series, right. Therefore, this thingy, it has to start at 1, because I don't know what the hell this is at 0. Converges. Yeah, that's a problem. Converges by comparison to a known p-series. It's known to converge because p is 2. That's all. Okay, then. What about this? Yeah. Yeah, that would be unfortunate. Okay, well, good question. I think Patrick brought this up too. What if we did 1 over n? Now, n is poly, right? So this is bigger than poly, so this is still correct. But this test is inconclusive. Why? Because this diverges, and this is smaller than something that diverges. Well, thanks a lot. I knew that. Everything's smaller than something that diverges unless it diverges too. So it doesn't prove anything. The test fails. So if you prove that your series is smaller than something that diverges, that doesn't help. If you prove your series is smaller than something that converges, that helps. So this is more helpful. And vice versa. If you prove something is bigger than something that converges, doesn't mean it converges, does it? If this converges to, like, I don't know, a half, and this is bigger, what does it converge to? I don't have to know what it converges to, but does it have to converge? No, it could blow up too. I don't know. If you show that this is always bigger than something that diverges, if this blows up and this is bigger, it's got to blow up too, right? So for the less than case, you want to show both are convergent. For greater than case, you're going to show both are divergent. Any other case does not help, like this doesn't help. Less than a divergent? Yeah, so everybody is. If you could, right? Everybody's less than a divergent if you converge. I'm trying to show convergence, right, aren't I? So that doesn't help. So this is helpful. All right, so pick something that's helpful. Okay, here is a free response question. Are you ready? And this really shook everyone up. In 1975, I forget which question was. 1975 BC, I'm going to guess, 5. I'm not sure. I know it was 75 BC, so whatever. Okay? Show this series to converge or diverge. Now, what's different with this about this series than any other series you saw today? Victor, you're saying what? Well, there's 3 parts to it, yeah. But what's the different part? How about that? What hasn't been here before today? What haven't we seen today that's here? The negative. This -1, right? If I plug in, I don't know. Let's say I could start with n equals 0, I suppose. Start with n equals 1. If I plug in n equals 1, what does it mean? Well, 1 plus 1 is 2. -1 squared is positive 1. Right, so it's an alternating series. It changes sign every other term. All right, so some are really adding, some are really subtracting, some are really adding, some are really subtracting, right? Okay, I don't know how to prove convergence of an alternating series. I can prove absolute convergence. What about the absolute value of that thing? Can I prove the absolute value converges? Now, notice that's different. That's every single term is in essence adding, right? So I'm going to make it worse, okay? If I make it so that instead of every other term is subtracting, I make every single term add, and I can show this converges, then that must converge to something. Not the same thing, but something. Okay? That's called absolute convergence, right? If I can prove an alternating series converges in absolute value, it converges absolutely. That's a difficult thing. This may converge by itself, but absolutely, that's hard. But if this does, so does this. This is harder to converge than this. If I can show this converges, I showed that converges. And that was the game plan. There's 2 kinds of convergence for alternating series. There's conditional and there's absolute. Conditional means it can converge just the way it is. Absolute means it can converge the harder way. This is hard. All right, well, can you use the comparison test to show this? What do you think? Compared to what? Now, remember, if you were trying to show convergence, you want to make this thing smaller than this thing, right? So you make the denominator bigger or the numerator smaller, or both. What am I going to do to the top? Leave it? Change it? Okay. It's got to be compared to this. So I'm going to leave it or change it. I'm going to leave it or change it. I'm going to use NN-FEPL to help me make this bigger, because I want a less than, so this side is bigger, right? I'll use NN-FEPL to make the top bigger, or I'll use NN-FEPL to make the bottom smaller, so the whole quotient's bigger, so I can do this. If I'm trying to show convergence, I don't know, maybe it doesn't converge, I don't know. By the way, it passes Cauchy, doesn't it? NN-FEPL, right? Exponential over Pauli, bottom heavy. So it passes Cauchy. So let me see if I can prove convergence. I don't know, maybe. What if you leave the numerator alone and you change the denominator to a Pauli? What did I do? I changed an exponential to a Pauli. Now the denominators, how do they compare? Is this bigger than it was? Is it smaller than it was? The denominator is smaller, and then FEPL, P is smaller than exponential, right? Power is smaller than exponential. So, but why was that a good choice? So that's 1 over n squared. That's a P series where P is 2. Okay. Did you have to do that? No. What if I changed the numerator? Now what did I do? Did I make the numerator bigger? Or did I make the numerator smaller than it was? Bigger, because exponential is bigger than Pauli, right? But why is this nice? That's r equals 2/3. Geometric series of r equals 2/3. All right, so I'll leave it like that. There you go. Okay, therefore, the original series converges absolutely by comparison to a known geometric series. To a geometric series, it's known to converge because R is an absolute value less than 1, it's 2/3. You got to be able to name the R if you're using a geometric series. You got to be able to name the P if you're using a P series. Okay? Is this terrible? See, this really sums up the whole game. Convert the numerator to something bigger using NN Feppel, or the denominator to something smaller, and you're going to get this. If you can do that, you can prove convergence. Vice versa. If you can make it so that the numerator is smaller or the denominator bigger, and you end up with something divergent, you're going to show divergence here. Okay. Try that again. It's top heavy, so right away it fails. Cauchy, divergent by Cauchy. Or fails, divergence test. All right, same thing. That's all you have to say. All right, that's top heavy because NN Feppel, this is the top of NN Feppel. This is going to be top heavy for n sufficiently large. Infinitely many n's will be bigger. N to the n will be bigger than factorial. Yeah? You could be more descriptive of what's going on. This is probably sufficient because this is usually part of a larger problem, a power series problem, where this is just a little piece of it. So they probably won't expect you to get too crazy for this. But I'm trying to make sure that this part's easy when we get to it next week, when we need it in the next unit of power series. Okay? So I'm trying to make this part easy. Alrighty. How about, let's see here. Let me think. Okay, how about this one? Alrighty. So does it pass Cauchy? Is it bottom heavy? Okay, so it passes Cauchy. Does it converge? Think, for n huge, what is this really acting like? For n huge, remember rational functions? The important part is the leading term. 4n over n squared. What's that like? 4 over n, right? Or 4 times 1 over n. This is divergent, right? My instinct here is that I can prove this is divergent by comparison to something. So do I want a less than here? Is that what we usually do for convergent? What do I want here? I want to show it's greater than something that I know diverges. If this blows up, that blows up. That's what I want. Okay, play the game. I want to make this fraction smaller. In other words, the numerator smaller and the denominator bigger. Can I just do that? Isn't the denominator bigger? Well, maybe not at n equals 1, but for infinitely many n, I could probably state it is true at 2. Sometimes you have to play with the lower limit. See, we're interested in the tail, right? If this thing converges, it goes crazy, and then it converges to something in the tail for infinitely many terms. That's what I care about. I don't really care about what happens here, right? If infinitely many terms add up to something convergent, good. If it diverges, good. But the infinitely many terms is what I'm interested in. So if I chop off the first few terms, I don't care. That's fine. Alrighty. So why is that good? She's out. Sorry. Why is that good? Well, because what did we just say this is? Yeah, that's just 4 times the harmonic. That's it. Therefore, the original series, well, I changed it up a little bit. Starts at 2 instead of 1, big deal. Diverges by comparison to n harmonic. They get a little crazy about this. Why is this n harmonic and not the harmonic? There is a difference. The harmonic is 1 plus a half plus a third plus a quarter plus... Is that what I have? No. It starts at 2, and it's times 4. So it's an harmonic. It's not the harmonic. But it still behaves like a harmonic, right? So they get a little crazy about this. Don't say the harmonic unless it's 1 plus a half plus a third plus a fourth. Okay? I don't know why they get crazy about that, but they do. How about this one? Ln, 1 over ln n. What if I did this? What did I just do? According to NN Feppel, I replaced the bottom with something bigger or smaller? Bigger, so the whole fraction is smaller. And you know this. Who's this? This is an harmonic. It doesn't start at 1. Almost the harmonic, right, if it started at 1. This is an harmonic. It blows up. This is bigger, so divergent. Done. Okay? So if you can't use the integral test, you might want to use the comparison test. Okay, tomorrow you guys are off with a bracket. Wednesday is the ratio test. Thursday is the pre-test for our real test on Friday. Alrighty then. Wednesday we're doing a ratio test. It's another test. The integral test, the comparison test, the ratio test. Okay. So, alright, bye-bye, FTP site.